Objectives for today. By the end of class, you'll be able to define and describe an atom, so you'll be able to tell me what it is and what its parts are. So you're well on your way to that with our starter on Friday. You'll be able to explain how molecules and compounds can form, and you'll be able to tell me the difference between a molecule and a compound, as well as you'll be able to tell me the difference between calorie spelt with a lowercase c and calorie spelt with a capital C, because there is a difference. All right? So, in order to understand the chemistry of food, which is our goal for this chapter, we have to first understand basic general chemistry. Atoms is where we have to start then. So, atoms are the building blocks of all matter. Everything on Earth is made up of atoms of different elements. There's 118 elements that we have discovered. Okay. And atoms are made up of three parts, okay? Protons, which are positively charged particles. Neutrons, which are particles that don't have any charge. And electrons, which are negatively charged particles. So these are arranged with the protons and the neutrons in the center of the nucleus, and then the electrons out there orbiting the nucleus. So this isn't a perfect picture, but it's a decent diagram for you to see how the electrons, some of them are closer to the nucleus than others, and they're also spinning around out there in space, moving every which direction, right? Different particles contribute to different properties of an atom. Protons contribute to the mass and the charge of the atom, so they have a positive charge and they have a mass, and they also determine which element it is, and this is important. All atoms of the same element have the same number of protons. Okay, so all atoms of hydrogen have 1 proton. All atoms of iron have 26 protons. Okay, so changing the number of protons changes what element you're dealing with. Neutrons contribute to the mass of the atom. They're also important because if you know that like charges repel each other, right? If you put two positive things near each other, they're going to try and push each other apart. So in order to keep the nucleus stable and not have all those protons flying apart from each other, you have to have the attraction forces from the neutrons. So they are important, even though they don't contribute to the charge of an atom. And then electrons contribute to the charge of the atom, but not to the mass, because electrons are very, 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 very small and have almost no mass. In order for an atom to be neutral, the number of protons and the number of electrons has to be the same, which most of you were able to identify from the little lab that we did on Friday. Molecules and compounds. Individual atoms are not usually found alone by themselves in nature because most of the atoms on the periodic table are not super chemically stable by themselves. Okay? Instead, in order to become stable, most atoms are going to do one of the following things: lose electrons, gain electrons, or sometimes they will share electrons. Anytime an atom loses or gains electrons, they become ions. We define ions as any atom or any group of atoms that has a charge. Molecules and compounds can form. They are two separate things. Okay? So a molecule is a group of atoms that the atoms can either be the same as each other or different elements. Okay? So, for example, if you have two atoms of oxygen bonded together, that's a molecule. If you have two atoms of hydrogen and one atom of oxygen bonded together to make water, that's also a molecule. Compounds are a combination of two or more elements that are different. So in order to be a compound, you must be different from each other. So we use the word molecule as a general term for a group of atoms. We can use it to describe any group of atoms. But if we want to specifically identify to somebody that this group of atoms is different from each other, not all the same atom, then we use the word compound. So what I have written down here at the bottom, all compounds are molecules, but not all molecules are compounds. Okay, so a molecule of water, because it has two different elements in it, hydrogen and oxygen, is a compound. A molecule of oxygen with two oxygen atoms bonded to each other is not a compound because they are the same atom. They are not different. Okay. So when in doubt, I would use the word molecule because it's a catch-all. It fits all of them, right? And so that's why you'll hear me use that word a lot of times. And then if I want to be more specific, I can use the word compound if it applies. So now that we understand what compounds and molecules are, let's talk about how they're formed. Okay? We form groups of atoms in two ways. One, by sharing electrons. So in order to make water, two hydrogen atoms, which each have just one electron, share that one electron with an oxygen atom. And so because they're sharing those electrons, they're joined together, they're connected, and they form a molecule. The other way to form an atom is by being attracted to the atom by an opposite charge. So in order to make salt, you need a negative chlorine ion and a positive sodium ion, and they get attracted to each other because they have opposite charges, right? So what happens actually is that the sodium ion is a sodium atom, and it gives its electron to the chlorine atom, and as a result, the sodium atom becomes positive and becomes an ion, and the chlorine atom becomes negative and becomes an ion, and then they are attracted to each other because of that difference in charge. And that is how we get a molecule of salt. Chemical reactions. When atoms do join together, they form what we call chemical bonds. Okay? So those sharing of electrons or that charge attraction, it forms a chemical bond, and those chemical bonds store energy for that molecule. When you do a chemical reaction, what you're really doing is breaking those bonds and rearranging them to make new ones. Usually, this requires some kind of activation energy. So that means you have to put a little bit of energy in to get it rolling. So think about the fact that in order to start a fire, you have to light it with a match, right? You have to put a little bit of energy in, but then the amount of energy you put in with the match, you get way more back out of the fire, right? So that's a good example of activation energy. It's required to initially break those bonds, but then when new bonds are formed, those new bonds hold less energy than that initial bond, and as a result, there's all this extra energy, and that energy has to be released somehow. So some examples of where you might see that energy being released are when you light a campfire, you get light and heat from it, right? Light and heat are both energy, so what you're feeling is the energy being released by burning those wood chunks, which is really breaking down the bonds in that wood and releasing that energy. Same thing for light and sound from a fireworks display, okay? Light and sound are both types of energy that are being released by that firework. And then the last one is if you put your hand to your face, you'll more than likely feel some heat coming from your skin, either from your hand or from your face, depending on which one's warmer. And that, the energy that your body has in order to keep your temperature stable, okay, that's energy released from the food that you eat. All right, now let's talk about food, because that's what this chapter is going to be about, okay? We're going to be discussing food as a type of fuel. So in order to run a machine, you require to put energy into that machine, right? You wouldn't expect your truck to run if you didn't put gas in it. Well, the same thing is true of humans and all other organisms, but in the case of humans, our fuel is the food that we consume. All food that we eat has chemical bonds in it, and when we break down and rearrange those chemical bonds during the process of digestion, that energy is released, and then our body can use it for a variety of different things, okay? Like keeping your heart pumping and letting your muscles work and breathing and keeping your body at a certain temperature so that everything in your body functions correctly, okay? All of those things require energy, and we get that energy from our food. The last thing we're going to talk about is the unit we use to discuss energy, okay? There's a couple of units that scientists use. The first one is the joule. So if you've ever taken a class where we talk about, force and energy, you've probably heard the term joule, okay? The one we're going to talk about in relation to food is the calorie, okay? The calorie is the amount of energy needed to increase the temperature of 1 gram of water by 1 degree Celsius, okay? That's how we define a calorie. Energy that's listed on the back of your food labels is also listed in calories, but you'll notice that it's calories with a capital C, which is different, believe it or not, than calories with a lowercase c. Don't know why scientists and food people couldn't get on the same page, but a calorie with a capital C is actually equal to 1,000 lowercase calories. Okay, so a calorie that you see on the back of your food is actually 1 kilocalorie, since the prefix kilo means 1,000. Okay, so just keep in mind that when you look at the calories listed on a food label, you're actually looking at a kilocalorie and not just 1 calorie. So the calorie on the back of the can would be enough to raise 1,000 grams of water by 1 degree Celsius instead of just 1 gram by 1 degree Celsius. Okay? All right.